When we talk about quantum mechanics in Chem 1, we're going to talk about orbitals, various wave functions that arise from taking an electron, bounding it about a nucleus by an electric charge, and saying the combination of the wave properties of the electron and those boundaries give us energy levels that have different spacings. Those energy levels will be 1 to a wave function, energy level 1, wave function number 1, energy level 2, wave function number 2. They might be the same energy, that is, wave function 3 may have the same energy as wave function number 2, but they'll all have different energies and associated with different sets of quantum numbers. So let's look at those quantum numbers and the energy levels for an atom. The principal quantum number n, again, runs just as the integers, 1, 2, 3, and it gives you the overall energy, as we said, just like in a particle in a box, of the hydrogen wave functions. So the wave functions have energies that are actually look quite simple. Z squared, that's the charge on the nucleus. So for a hydrogen atom, that's 1 proton, so that charge is 1. N, the quantum number, and a constant. This is Rydberg's constant. It has a value that we can calculate and a value that we tabulate. That value is 2.18 times 10 to the minus 18th joules. You could also express it in terms of hertz, or multiply by Avogadro's number and express it in terms of a mole of hydrogen atoms rather than just a single hydrogen atom. So how does this look if we plot energy levels versus quantum number? What does this kind of energy expression give us? Well, n equal 1 is the ground state, the lowest energy state. It's not n equals 0. Remember, there is no n equals 0, and a lot of people like to associate ground with 0. But in this case, the ground state has n equal 1. That has an energy of 1 squared for a hydrogen atom over 1 squared times Rydberg's constant minus R infinity. Why are the energy levels negative? Why do we do this negative energy level? Well, whenever you have energy, you have to give your energy relative to something. And the relative to something, we say, for atoms is the electron and the nucleus infinitely far apart and at rest. So that's the 0 in energy. When you bring the nucleus and the electron closer together, they become more stable. They go down in energy. So when you're at 0, the only way to go down in energy is to go to negative energy values. So we're going to use a negative system to describe this. If we bring in n equal 2, we still have 1, the charge of the nucleus. We're still talking about a hydrogen atom. Charge of the nucleus is still 1. N is now 2. Square that, you get a quarter of a Rydberg minus R infinity over 4. A quarter of a Rydberg down from 0, which is the ionized state, the electron and the nucleus separated in space. And you can continue to do that. You can look at energy levels 3 through infinity. When you get to the infinite quantum level, that is ionized. And of course, you don't even have to go to infinite to get ionized. But the high levels of n are systems where the energy is about 0. And since it's 1 over n squared, you don't have to go to very big n for this energy to get very, very small and close to 0 very rapidly. The ionized state is the 0 energy state for the hydrogen atom.